In the tetrahedral complexes, the tetrahedral arrangement of 4 ligands surrounding the central metal atom or ion may be visualized by placing the ligands at the visualized by in tetrahedral complexes. The tetrahedral arrangement of the 4 ligands surrounding the central metal atom may be visualized by placing the ligands at the alternate corners of the cube. At the alternate corners of the cube. In the tetrahedral complexes, the placement of ligands may be visualized by placing the ligands at the alternate corners of the cube. For example, we know the tetrahedral complex looks like this. One is here, one ligand is here. Yes, one ligand is like this one. So if I make a cube and try to visualize the ligands, yes, so suppose this is one ligand present at one corner. Now leave one corner, one ligand. Now one ligand, leave one corner, one ligand. This is how, and this is central metal atom. Yes, so it's connected. Now suppose this is our x-axis, this is y-axis, and your z-axis. This is your z-axis. This is y, this is x. These are the axes. Now if we see these ligands, I have told you in this case also, what is x and y? dxy are these ligands. And here, if you see dxy, if you see here, so here ligands are approaching to dxy ligands. Yes, or to dyz ligands, or to dzx ligands. Yes. So basically this time T2 orbitals. But in this case, in tetrahedral, it's assumed that the ligands, we can say the orbitals, they are not degenerate, means they are not similar. So this time the d orbitals generate means similar, but there this time we call them T2, and these are E2 orbitals. E2 orbitals. This time T2 and E2. Yes, T2G, EG. So it will be E. Why? Because this time the orbitals, they are not degenerate, means yes, in octahedral complexes the orbitals are degenerate, but here they are not. So what happens in tetrahedral structure? If we write some theoretical points so that you will remember the theory. In the tetrahedral structure, what happens? None of the d orbitals point exactly towards the ligands. In the tetrahedral structure, none of the d orbitals, it points exactly towards the ligands. In the tetrahedral structure, none of the d orbitals point directly towards the ligands. When the ligand approaches, what happens when the ligand approaches? Yes, when the ligand approaches, it is more close to, as I've shown in the picture, it is more close to dxy, dyz and dzx. It's more close to dxy, dyz, dzx, right? In comparison to dx square minus y square and dz square and dz square, right? Because these, why? Because dx square minus y square and dz square dx square minus y square and dz square, they are along the axis, so therefore dxy, dyz and dzx, they feel more repulsion. They feel more repulsion, right? That is why in tetrahedral complexes the splitting order is just reverse. So we have this, suppose we have this 5 orbitals. Yes, when the ligands are very far away, yes, then simply energy. Now what happens here? E2 orbital, they are not E2, they are E orbitals, right? E and E2 orbitals. So now what is the energy? It's very center. What is this? Average energy is goes to 0. So here it's minus 3 by 5 del O, or, and here plus 2 by 5 del O, or minus 0.6 del O, or minus plus 0. Del O, right? This is del O, right? This is how you have to do this. I hope it's clear to you how to calculate the value of CFSE in case of tetrahedral species. Remember one thing, it's because tetrahedral, so we'll write it as T, del T, del T, del T and T. So remember one thing, the relation between del T is equals to 4 by 9 of del. This is what you have to remember. Next what you have to do is, now here just one thing you have to remember, in tetrahedral no pairing of electron takes place because due to low splitting energy. Tetrahedral complexes, whether you take strong field ligand or you take a weak field ligand, yes, no pairing occurs. No pairing occurs means firstly you have to fill all the electrons significant, then you start the pairing. Next what you have is, suppose if I ask you, okay, D1, find out the CFSE. How you will find? This is 1, we have E orbital, and this is T2, 1. For 1 CFSE will be minus 3 by 5 of del O. Yes? 3 by 5 of del T. If I ask for D2, it will be minus 3 to the 6 by 5 of del T, and for D3 it will be minus 6 to the for D3 we have to, for D3 the electron will go in T2 orbital. Suppose I ask you for D3. What will happen in D3? Yes, splitting will occur and we have E orbital and we have T2. So 1, 2, 3. We have 1, 2 and 3. This is minus 3 by 5 of del T plus 2 by 5 of del T. So CFSC 3 to the 6 minus 6 by 5 of del T plus 2 by 5 of del T. It will be minus 4 by 5 of del T. Similarly, you can find the value for D4, D5, D6, D7, D8, D9 and D10. Yes, for octahedral complexes we have already discussed all the values. For tetrahedral you can do it by yourself. I'll give you an example quickly. If I ask you find out for D6, 1, 2, 3, 4, 5, 6. We have E orbital, we have T2. So this is E, this is T2. 1, 2, 3, 4, 5, 6. Now what will be the value? It will be CFSC. Minus 3. 3s are 9 by 5 del O plus 3 2s are 6 by 5 del O, which will be minus 3 by 5 del O. This way you can calculate the values of all the CFSC. Suppose if I ask D8, how will I find D8? By mistake, I'm writing del O everywhere. It's del T. Remember, okay? Because last time we were doing del O, so it has become into the, we keep on writing same thing. It becomes a habit. It becomes a habit then. So that's why I was writing it del O again and again, but it's reality del T. And del T equals to 4 by 9 of del O. Yes, D8. So it's E2 and T2. So 1, 2, 3, 4, 5, 6, 7, 8. Here also 1, 2, 3, 4, 5, 6, 7, 8. So CFSC minus 3 by 5 into 4 del T. Yes, plus 4 into 2 by 5 of del T. Yes, so 4 is a 12 minus 12 by 5 del T plus 4 is a 4 to the 8. 8 by 5 of del T. So it will be minus 4 by 5 of del T. This is how we do the questions. I hope the CFT lectures are clear to you and you have enjoyed finding out the CFSC's value. In the next video, we will be coming with the middle carbonyls lecture. And we have also color and coordination compounds. Till then, keep watching. See you in the next lecture. Bye-bye.